Now we are going to discuss chemical shift. This is very important video to understand nuclear magnetic resonance spectroscopy. You please watch this video very carefully and you listen word by word. I mean whatever I'm telling you, you just listen very carefully to understand chemical shift, because this is very important for the nuclear magnetic resonance spectroscopy. Now, up till now, we have seen that different kinds of proton present in the molecule, in organic molecule, and different kinds of protons we can decide by just finding out its environment. In fact, its electronic environment. So we can consider its electronic environments, means we can consider its electrons present in the bond. That may be sigma bond, that may be pi bond. That is called electronic environment. So you consider, or we consider, electronic environment to decide different kinds of protons present in the molecule. And each type of proton present in the molecule gives NMR signal. So total NMR signals obtained are actually equals to the different kinds of or the same kind of protons present in the molecule. So the position of the NMR signal tell us about the kind of proton present in the molecule, because different kinds of protons have different electronic environment. That word is important, electronic environment. So on the electronic environment, our chemical shift is actually decided. Chemical shift means where that signal is obtained, that is decided according to the electronic environment of that proton. Now, coming to the next point, please listen carefully, that the electrons present in the bond, as I mentioned, we can call it as the intervening electrons. Actually, maybe sigma bond, maybe pi bond, they are circulating. They are circulating means they are also acting as a tiny bar magnet, because electrons are also having a negative charge, means they are charged particles, and in presence of external magnetic, they are producing a small magnetic field just like protons. Now we have to consider the magnetic field generated by the intervening electrons. So that electrons are around the protons and they are generating small magnetic field. This magnetic field we can say is a B0, which is also called induced magnetic field. This induced magnetic field because of external magnetic field. So we have external magnetic field B0 applied to the molecule in the instrument, and intervening electrons which are circulating generating magnetic field which is also very small. We can say this is B0, small B0, and this magnetic field is called induced magnetic field. You understand induced magnetic field. Now the induced magnetic field means, which is also very small, can act by two ways. One, this induced magnetic field can oppose or can reinforce the applied magnetic field. Now we have applied magnetic field in one direction, and this small induced magnetic field due to circulating electrons, that is B0, which is very small, can act by two ways. Either this induced magnetic field can oppose B0 means applied magnetic field, or this induced magnetic field can add or reinforce to the applied magnetic field. In that case, if this is opposing, our proton will feel less magnetic field, means less than B0. So the protons now feeling less magnetic field because induced magnetic field opposing that field. In another case, it is depend on the orientation of the molecule, depend on the geometry of the molecule, and many other structural factors we need to consider, that we'll discuss in next video. Now if it is opposing, you just listen. If it is opposing, the magnetic field, now the magnetic field experienced by the proton is less than B0. That will be less by this value. And if the magnetic field means applied magnetic field is opposed or reinforced means added due to its structural factors, then the magnetic field experienced by the proton is greater than B0. You remember this. Now coming to the next point, when the induced magnetic field opposes the applied magnetic field. Now opposes means B0 minus B0 magnetic field, the proton is said to be shielded, just like that shield, as if that proton is shielded by the induced magnetic field. Suppose the direction of the magnetic field is this one, and the induced magnetic field actually protecting our proton from the external magnetic field. So the field experienced by this proton is less than B0. We call that protons are shielded, or that proton is shielded. Now what is required? We have a constant radiation, we have a constant energy. We have a constant energy from the radio wave region, and we need to bring that proton into resonance. What is important? A constant energy means you can see here delta E is constant. This is constant, the energy of the radiation, that is h nu. H nu is constant, suppose, and this gap we expect, but actually when the applied magnetic field is opposed by the B0 induced magnetic field, you can check here in this diagram, this is a decrease, so the delta value is decreased. Now h nu is constant, delta E is decreased, and as I mentioned earlier, according to physics law, that for the absorption this delta E must be equal to h nu. That means delta E must be equal to h nu to get absorption, or we can say the proton is in resonance. So what is required? Here actually you can check this diagram. The applied magnetic field is reduced, and you know this gap is directly proportional to the applied magnetic field, but it is reduced by induced magnetic field. So the gap is reduced, and this h nu is constant. So if gap is reduced, how that resonance is possible? It is not possible. That means our proton will not absorb energy, because that energy is not matched with this energy gap. So this is not actually matched, and proton will not absorb, or proton is not coming into resonance. So what is required? We need to increase this gap up to this one. Now you can check here, if this is this one, if this is this, if I extend this, you can check here, this gap is more. So this gap is actually reduced by this quantity. Now what is required to increase this gap? This gap is actually directly proportional to the applied magnetic field. If you want to increase this gap, we need to increase the magnetic field. We need to increase the value of B0, because our instrument is working on the principle that we can change the magnetic field, we cannot change the value of h nu. We cannot change this value of radiation or energy of the radiation. So we need to increase the magnetic field, and when the proton is shielded. I hope you understood the first point, this first point. Now I am coming to the next point. That if the induced magnetic field is reinforcing the applied magnetic field, means added. Now you can consider this diagram. Now B0 is applied magnetic field, and this small B0 you can see, this is an induced magnetic field due to circulating electrons. It is added in the value. Added means the magnetic field experienced by the proton is more. Is more means this gap is more. If this gap is more, h nu and this gap is not actually matching. And if it is not matching, there is no resonance. If there is no resonance, there is no NMR signal. So what we have to do? We have to decrease this gap. We have to decrease this gap, and we have to decrease this gap up to this level for the resonance. So what we are doing? We are actually reducing the applied